Hello and welcome to episode 68 of Codebase Alpha, and today we're taking a little break from the shader stream we've been doing every Monday, and we're going to look at the Z80 emulator, Project Z as I call it. So we're going to build an emulator for the Z80 chip. The ultimate aim of that is to make a reusable NuGet package for it. It'll include a disassembler and some kind of memory visualization tool to help you step through programs. And then we'll figure what we're going to use that for later on. Maybe we're going to emulate a Game Boy or a ZX Spectrum, or maybe we're going to do something completely different, who knows. But the first thing we need to do is actually get a chip. So an emulation of the actual chip. So that's what we're going to work on today. Now, in the last stream which we did on the Z80 emulator, it was a bit of an introduction. And I was working on the 8-bit load group of Opcodes. And there's still quite a few of those to code, and then there's a 16-bit load groups to do. So they're a bit samey, so not something that's overly interested on the stream. So I thought what we'd do in this stream is add some arithmetic codes to it, some 8-bit arithmetic, and maybe some logical if we get some time. So let's get a bit of music going to kind of ease us into the coding. There we go, bit of relaxed daily. Hopefully that's coming through okay, not too loud. And let's pop over into the code and see what we can see. Okay, so here we are. We're in the Z80 class, and what this is made up of. It's actually I've defined it as a partial class, and I've split the actual code across 3 different files. So we've got the Z80 main class here, main class file. Then we've got Z80.addressModes, which is the coding for how data is addressed and pulled back from random access memory. And then we've also got Z80 instructions, is where I'm coding all the actual instruction logic. And we've got a test project here, Z80.tests. And currently we've got some tests here for make sure that my functions for working with the register flags, which I'll describe it shortly, is working okay. And then we've got our 8-bit load group tests, so quite a lot of stuff here. And what this is using is a system called, or a framework called Fake It Easy. It's the XUnit test framework with Fake It Easy actually on top of that. And what this is letting me to do is actually define little program segments and areas of memory, and then it enables me to read and write to that kind of that fake program structure or fake piece of RAM using these faked objects. So you can see we've got a faked read and a faked write, and this is really quite powerful. And those 2 lines basically gives me a fake access to this dictionary here, and it should act exactly like it will in operation when it's actually reading and writing to fake RAM. And then I was going to do all the assertions down here. But one first thing I want to do is actually upgrade Fake It Easy, because there's a new version just come out, I noticed. So let's just update that. So we'll go over to Manage NuGet Packages, and we should find there's an update for Fake It Easy. Indeed there is. So it's 5.3. So let's upgrade to that. There's actually a XUnit minor upgrade there as well. So we might do that as well. So let's go up to Fake It Easy 5.3, and we'll upgrade the XUnit framework as well. And we'll do the test runner as well. Okay, so that's those updated. Now there's a Microsoft Test SDK that's got an update as well. Let's try that. Let's upgrade that as well. And see, we can make sure we build after this. And we can always kind of drop back into the previous version if we have to. Okay, let's just see if we can build. Yeah, so we're okay. So we got the latest version. I don't know what this coverlet collector is, so I'm going to leave that off for the moment. The other thing that I did off air was to upgrade our Z80 project here to .NET Standard 2.1 and enable nullable reference types, which I've done here. So this is now we're using C#8, so we get access to nullable reference types as part of that. And so all my reference types now are non-nullable. They can't accept nulls unless I actually make that design decision to let them accept nulls, which is quite good. Now, the one thing I will point out is that currently we have a private variable here, which is for the bus here. So this is currently we don't have a concrete implementation of our iBus interface. We're still playing with kind of fake ones. So I'm forced at this stage to set it to null, and the syntax to force it to accept a null is this exclamation point here after the null. So we have to have a null value for the moment. That will eventually go. So this is just a temporary situation, and then down in the connect to bus here, this will allow me to actually pass in a bus implementation, which will be open to users to create, and I will create a default bus implementation, which will be the one which will be instantiated in this private variable, the default bus. We can then change it with the connect to bus command or connect to bus method. Okay. There's another C#8 feature which I very much enjoyed using, and that's over in the Z80 instructions, and that's this. You may not have come across this, or you may well have. It's a switch expression. So here what we're doing is saying that this method here is going to return one of these registers depending upon what the value of src passed in integer was. And here we say if it was 0 it's B, 1 C, 2D, etc, 7A, and then anything else is going to just return the value of 0, which may be an issue, but we'll cross that bridge when we come to it. That proves to be problematic, but in fact these are the only values we should be getting from our operation codes. So I think that's really a really neat kind of little construct there. That's the switch expression. Okay, so we're adopting this test-driven kind of development approach. So we're going to start off with creating tests for the command we want to create. But first we need to do some kind of basic wiring for the test. So we do need to have a kind of a stub function, and in order to get the stub function, which is going to fail the test that we run, we need to do a bit of setup. So if we go over to our Z80 class, you can see here we have a number of dictionaries which represent all the operation codes that are available to us in the emulator. We've got root instructions, which are single byte operation codes, and we've actually got extended operation tables which are dual byte. So this is DD 36 and DD 46, etc. And then we've got another one here which is FD 36, FD 46. Those are dual byte ones, and in fact there are some more as well. There's ones beginning with CB, and then there are 3 byte instructions as well. So we're adding these as we need them. So let's go and have a look at the user manual, because we do need to create an entry into our root instructions in order to actually get a test which will fail beyond the fact that it doesn't compile because the method doesn't exist. So let's have a look at the documentation. So we've got a really good resource here. This is the Z80 CPU users manual, and this is the command we're going to start off with, which is add a, n, which is add the value n to whatever value we have in a register called the accumulator. So A is one of the set of registers that we have to play with in the Z80. It's an 8-bit register, and it's where we, as the name kind of implies, where we accumulate results from arithmetic operations. So largely we deal with the A register. It's going to hold the result of our operation, and here we're simply adding a constant value n to that accumulator, whatever's in there at the moment. Now it's actually operation code C6, which it says here. It's a single byte code, and immediately following it is going to be the actual value of n, and it's an 8-bit value. So we're dealing with 8-bit arithmetic here. Okay, so we're not, although the Z80 can do 16-bit arithmetic, we're not going to do that today. We're just going to look at the 8-bit. In fact, the arithmetic and logic unit within the Z80 is actually 4-bit. It's quite an interesting kind of architecture, and the fact that it's 4-bit does have implications on the register flags we need to set. But as a whole, the Z80 is an 8-bit processor, which is capable of operating with 16-bit words through special commands. So what this data sheet is telling us is that what we're going to do is take A plus n and put the result into the A register, the accumulator. The operation code is add, and the operands are A and n. It's C6 in hexadecimal, and it's going to take 2 machine cycles, which is made up of 7 T states, 7 clock ticks. So that's 4 ticks to evaluate the operation code and 3 ticks to pull back the operand and actually calculate the total and pop it back into the accumulator. And we've got here all the condition bits for our flag register, which is going to be set. So we need to kind of take care of those. But the first thing we need to do is basically set up a framework within our emulation that we could actually pass it the code in the first place. Okay, so let's do that first bit. So it's C6 is the command we want to do. So let's pop it into a realistic place in here. So C6 is going to be right at the end here. So let's just copy that instruction and let's pop it down here. So this will be C6, and it's add. So this mnemonic here is for when we write our disassembler, and it's going to be immediate addressing. So immediately following the opcode is going to be the operand. We've got 2 addressing modes here because some commands will literally have 2 addressing modes. So they will get an operand from one place maybe and store the results somewhere else, or that kind of thing. So we're only in this command we're only using the first addressing mode, but we do fill in the second one. I'll just default it to whatever the first one was. And we need to actually give this a function name, so we're going to say add an, and it took 7 clock cycles to actually run. So interestingly, it's not picked up these. It should be okay. It does know what those are. So add an is what we want to actually have. So let's go over to our instructions, and we're going to just copy this little, or copy that as well. We'll copy all of that. Just go down to the bottom because I've still got a fair few of these 8-bit loads and 16-bit loads to do, so give us some space. So we'll say 8-bit arithmetic and logic group. Okay, so our first command is going to be add a comma n, and the result of that is going to be a plus n is going to go into A, and flags affected, we're going to pop it does affect flags. So unlike anything we've done so far, we're going to be affecting our condition flags. So this is going to be add an, and we're going to simply remove all of that code there. So we're going to return 0. Okay. So now over in our Z80 class we should have picked up that function, and we have. Okay. Now that should be enough, I think, to get us working. Okay, so we can go now. We can go actually start our test-driven part of this. We've set up an opcode here which basically does nothing, and now we're going to write a test which says it should add 2 numbers together. So let's create a new class. This class is going to be called what should we call it? 8-bit. Arithmetic logic group should, like that. We need to spell that correctly. Let's just change the name of it. There we go. Okay, so that's a public class, and then we can go and just grab a few attributes here. So we want a fact. Let's go and copy that across. And then we bring in XUnit. We need to delete the flags unchanged because the flags should change. We're going to call it load A with three when adding 1 and 2 for opcode add an. Okay, so that's what we're going to do. We need to bring fake it easy in. The first thing we do is set up a fake bus. Remember, as I said, we don't have a concrete implementation of iBus, so we're only working with fakes at the moment. We will build one eventually when we decide what the architecture is. The iBus interface does need to change because we're not actually correctly kind of emulating what the bus would look like in a real Z80 microprocessor system. Basically, peripherals have ports, and you address the ports. At the moment, it's just a big 64K of RAM in effect. Okay, so we've got a. So I think what we need to do is to go and get some of the more advanced stuff down here where we write fake programs. So let's grab all this. Let's grab all of this instead of what we grabbed before. Bring that across. Okay. So flags unchanged we can get rid of because they're not going to be unchanged. In this case we don't need update memory, and we don't need we're not going to write to memory because the result's going to be stored, as you remember, back in the accumulator. Okay. So we're going to add 1 and 2 and make 3 is basically the objective here. Let's just get rid of this stuff. So in the accumulator we're going to assume that the value 1 is in there to begin with. We don't need any other registers apart from our program counter, and our program counter PC is going to point at the start of our program, which is 80 in hex, and here's the program start. So if you remember, it's C6 is the first command, and we want to add, we've got 1 in the accumulator, we want to add 2 to that, so 0, 2, and then the rest of the program is no operation, 0, 0. Okay, so that's our program. So this is add a and n equals 2, like that basically. Right, so we're now ready to actually run this. We need to say that we think that we should get 3 in the accumulator at the end of running that operation. And it's going to be CPU.a. Okay, so here's our fake CPU. We set it up with we're going to kind of initialize it with 1 in the accumulator, program counter pointing to the start location of the program, which is there. We connect up to our fake bus, and then we do give one tick of the machine cycle. So it's one machine cycle tick. It's in fact going to run the entire command. So it's not going to kind of really do the machine cycles. It's going to be one kind of, I've called it tick, but it's one way through the clock basically. In this particular case, add a comma n is going to take 7 t cycles, so it's going to stay in the tick method, and it's going to loop around 7 times to kind of to emulate that delay in it processing, and that's how we're going to use it to kind of synchronize with other devices. So who's in chat? As we got a couple of viewers in chat, so do make yourself known. If you notice on my viewer count, I'm actually 1 away from hitting my my target of 300 followers. So do make yourself known. Whoever's in the viewers in chat at the moment, that'd be great. Okay, so we've now got the command, and we should be able to now run this. Where's my test runner here? Let's open up these. Okay, if you run all the tests, it should obviously fail, because it's not, the accumulator is not going to have 3 in it. It's going to have 0 in it. So it fails, and it actually had 1 in it, of course, yes, because we loaded it 1 initially. So as we expected, it fails because we expected a 3. The actual value in the accumulator was 1, which was the initial value that started with. However, everything else passed. So that's good. So we can close these other ones down. We know they pass. Obviously, the support of the tests there mean that if anything we do were to break something which already works, we get alerted. And this actually happened to me a couple of days ago. I made a perfectly correct change to my code, and 10 tests immediately failed, and they weren't connected with where the change I'd made. And I analysed that and found I was off by 1 error elsewhere in the code, but the change I made kind of highlighted that elsewhere, and I'd have missed that without the support of these tests. Okay, so that's our red part of red-green refactor. So let's now look at getting it green. So in order to get this green, we want to do the simplest thing possible that could possibly give us a passing test. And that is that we say, okay, so we want to get a value n, and we're going to fetch that, use fetch1. So that should bring that back from memory. So we need to pass in which operation table we're using. We're using the root instructions table. And that means it will pick up the correct addressing mode. So now we're going to get a value n. It's going to be a byte that comes back there, and we're going to say that what should we say? Var sum equals a plus b, and equals a plus n, like that. And then we're going to say that a equals sum. Okay, and we need to cast that as a byte. Okay, so there's the simplest code that could possibly work. We we go and fetch our value. We're in immediate addressing mode, as we pointed out when we went over to here. We set it up as immediate, and if you want to see what immediate addressing mode looks like, it simply says the address where we're going to get the value from is basically going to be, we're going to increment the program counter, and that's going to point at where the data is, which is obviously immediately after where the operation code was, and we load that into the absolute address private variable here. Okay, so that's our test. Well, let's run the test. So let's see what it says. Let's run the test. We're going to run all the tests, but we're only going to concentrate on this one. So now that's passed. And we might think, great, that's it, we've done it. Now we need to carry on and give the next command, but that's not quite right. If we go back to our operation, our user manual, look at the operation, we can see these condition bits. Jitter Ted, thank you for the follow. That's 300, so thank you so much. We've managed to hit 300 at last. So thank you so much for that. Let's have some Electric Elf hype for that follow. So thank you. Good to see you as well in chat. Never mind. Never mind. We do try to follow each other in the live coders, but sometimes you do miss people. So yes, thank you for the happy 300. Okay, so we need to kind of take these a step at a time. Okay, so let's have a look. So these are all the different kind of condition flags which exist within the Z80. In fact, there are two more which we need to take care of, and these are undocumented features, and we're going to do the undocumented features of the Z80 as well. So if we look through here, we have the sign flag S is set if the result is negative, otherwise it's reset. Otherwise, what that means, it's true if it's negative, and it's false if it's not negative. The Z flag is set if the result is 0, otherwise it's reset to 0. The half carry flag is an interesting flag, but that's set if there's a carry from bit 3, otherwise it's a reset. The parity stroke overflow flag is set if we overflow. So if we overflow 8 bits, if our addition is greater than 255, then we've overflowed the amount of data storage we have in a byte. So we need to set the overflow flag if that happens. N is to do with whether we're doing addition or subtraction, and it's not actually part of this type of addition or subtraction. It's for binary coded decimal, which is what the Z80 is capable of doing. So we don't really need to use it, but we're going to follow the instructions. We're going to reset N, and then we got a carry flag. So if we carried from bit 7 into bit 8, then we're going to set the carry flag. So we're going to take these one by one. Binary coded decimal, yes, just to Ted, it's wonderful stuff, isn't it? Yeah, this is going back a bit. So, but I think it's interesting. It's a relatively straightforward CPU to actually try and emulate. Say the whole project that we're doing now was inspired by Javid X9's 6502 emulation, which is part of his emulating the Nintendo Entertainment System, the NES. But I'm going to take it in a slightly different direction, and also doing a rather more advanced processor than the 6502. 6502 processor was the first CPU that I actually did assembly language for. But that was an awful long time ago. An awful long time ago. Okay, so let's take the first one. So we're going to reset the N flag. Okay, so that's fairly easy. So let's write let's add to this test. So for whenever we do addition, the N flag should not be set. So let's go over to our arithmetic here. So we're going to say, we're going to have an assert. So what's the best way of doing that? Let's go and look at commands we've got, instructions we've got over here. So we've got some, we've got check flag and a set flag. Okay. So this is not really a very good test, because we're starting off with all of our flags actually unset. They're set to false, but you know, it should be good enough to start off with, and just to illustrate the way we're going to actually do the command. So if we go over here, at the top of our 8-bit here, we've got some assertions. We want the end flag, and there it is. So we're going to assert that's false. Let's grab a hold of that, and this is going to be, we're going to have that every time we do an addition, and when we do subtraction, that's going to be a flag that's set to true. So this will actually pass now, because we haven't affected that flag in any way. So if we just run this again, we should see it still passes. Okay, it's going to run eventually. Okay, we've hit a yeah, my test runner is locked. It's locked the file, which is not a great thing to have happened. Oh dear. Yes. The last time this happened, I had to restart, which would be a problem, because that would mean the stream would have to stop. Well, I restarted the computer. Let's try just shutting down Visual Studio and restarting it and see if that frees it up. So my worst nightmare really is that file lock hitting, because that's something that's outside my control. Okay, let's give it another go. See if we can build. See if we can build this. No, it's for some reason it has locked that file. Oh dear. Okay. So I wonder if we can find out what is locking file. Windows. This internals file processing, that might be a bit too old. What's this one say? If you know the name of the application that has been used to hold the file before, you may want to check Task Manager. Yeah, I don't think it's that. That's why we can try Task Manager. So we're getting kind of sidetracked down, and yeah, lock files, it's great, isn't it? Let's have a look. It's going to be figuring out what it is. I don't know whether it's just to carry on without me tests. It's kind of a bit stupid in the way that we can't actually then run our tests, but it might be the only way I'm going to actually be able to carry on without restarting the stream, and I don't particularly want to do that. So which one of these could it be? Don't know what some of these things are. CPU.exe? CPU.exe? what that is. I think I'm going to continue just without the tests, which is a bit disappointing because the whole point of doing this was kind of test driven. But if we're going to be kind of forced into it, aren't we? Because of the I'll wonder if I should shut down both Visual Studios. Let's try that because I've got the bot running here. So let's just shut down both Visual Studios. Take that out of the equation. Run Task Manager again, so we haven't got anything like that running. Let's see. Let's now bring that back up. Let's see if that helps. I don't think it will because last time this happened, I did have to restart. That's in restart the computer. Could try clean us, but no, it's still grabbed it. So could not copy to that. It's used by another process. If we should, oh, test host. Test host has got it. So Task Manager. Let's see if we can find test host. I'm sure it says test host. Locked by test host. So, can we find test host in this little lot? Test host, let's kill that off. End task. Right. Now we'll try and build. And we can build. There we go. Okay, good. So I'll keep Task Manager open there just in case we run into any more difficulties. And we can get back on track. Okay. So over in our instructions here, we want to make sure that as a result of this, of doing this piece of arithmetic here, that we set the flag for the n, the kind of the addition subtraction flag. Make sure that's false. So we want to say set flag flags dot n for false. Okay, so that's our first bit of logic that we've added, and to do with that those flags. So let's just make sure that things still run. Run tests. We'll run it down here, and that's passed. Okay, one passed, no failed. Okay, that's good. And we've got a nice green tick here. So the next thing we need to look at, what else happens? Well, when we're adding 1 and 2, I don't think any other flags are going to get set. So let's have a look at the definition of what gets set. So S is set if the result is negative. So the result is negative if the most significant bit of the result is set, i.e. bit 7 is 1, then it's potentially a negative number. Now we know in case of adding two numbers together, two positive numbers together, they're actually not going to be negative, but if the most significant bit of the result is set, then we must also set the sign flag, because there's a potential that it could have been negative in terms of the logic of the CPU. We set the Z flag if it's 0. Okay, so the Z flag if it's 0 sounds like it's a very simple thing to do. Let's go and do that. So we want to say in this case that the Z flag is going to be 0. I it's going to be false. Okay. over to our instruction. What we'll do is we run our command, our test. Now obviously, as I say before, it's going to pass because they're all unset to begin with, but we'll start adding more complicated tests in a moment. So now we want our test which says that it is going to be set to 1 where we've got the result is 0. So let's add another fact. So load A with 0, we're adding 0 and 0. Okay, so that's a bit of a strange thing to want to do, but we're gonna add 0 and 0. So we're going to put n to be 0, and our accumulator is going to start off at 0, and we're going to say that the result should be 0, and our 0 flag should be set. Okay, well let's run these tests now. So that one passes, and then we'll run this one. And unsurprisingly, this one fails because it expected a true and it got a false. So now we're in the kind of the red part of the process again. So now it's we need to make it green. We're not going to go into the refactor just yet because refactoring it is going to be pretty simple, but also it's going to make our life a lot easier in terms of making sure our logic is correct for all the different operations we do. Okay, so in this case we're going to say if the sum equals 0, then set flag flags.z true, and we're going to have an else on there, else set it to false. Now we're doing kind of both, because if we may start off with that flag actually set. We're only kind of starting off with all of the flags unset because it's the beginning of the program, so we've just started the CPU up. If we go over to our user manual here, you say that it's otherwise it's reset. In other words, it's changed to false. Okay, so that's our logic there. There is a ternary expression available to us here, and we're going to take that option. So we're going to set it into a nice little ternary to make it nice and terse. Okay, so now we should be able to go over here, and remember this is the one that failed last time. Let's get this to run and see what happens. But we'll just run all the tests. So we should expect now a passing test. So 2 passed. It's down here at the bottom. Let's just run it individually so you can see that. There we go. So it's now passed with a nice tick against it. Now what we could do with doing is making sure that we build up these assertions as we go along, so that each time we know what we expect from each calculation. Okay, well let's deal with this sign flag next, shall we? Actually, I've got a test run over here. I'll just minimise that. I've got a test runner that's appeared over here, so let's pop that over there. It's going to shrink it down so it's not obscuring OBS. Okay, so what next? There's that sign flag, and the sign flag gets set if this is if the most significant bit of the result is 1. In other words, it's a potential negative number, and though as I say, we're dealing with positive numbers here. We're not actually going to get that set. When we start dealing with kind of adding a negative and a positive number together, i.e. in 2's complement, then we use the subtraction kind of command to do that kind of stuff, where negative results can genuinely happen. But adding 2 positive numbers together, we can't really get that. Okay, so let's write a test. Okay, so let's have another test here. Load A with what shall we say? So let's have a look at. Let's bring our calculator up. Go into programmers mode, binary. So if we want 0, 1, 1. So that's 127. So if we've got like 128, 129. So if we take 127 and add 2 to it, get 129. That should be fine. So if we say that, let's move that across. If we say that we're going to load this with 2, and we're going to, and then we're going to load, 7E into here. Uh, 7E into that. So that the result should be. Let's make it 7F. So that our result should be 81 in hex, shouldn't it? So this should be false. It's a non-zero result. And if we go over to our user manual, we're saying that if the result is negative, i.e. the most significant bit is set. So in this case, get rid of that. We're just going to say asserts true, and then it's going to be CPU dot S. Was it S? What was our sign flag? I'll just pop over to Z80 and go up here. Yes, it's S. So this is the flag register. We're going to bitwise and that with Z80 dot flags S, and I'm going to say that is equal to Z80 dot flags dot S. Okay. Right. So let's pop the same assertion up here. That's going to be false though, because in this case we're simply adding 0 and 0, so it's not a case where the result is going to have the most significant bit set. And here we're adding 1 and 2, so that also should be false. Okay, so let's run those tests. Run the run tests. There we go. So I think it's going to appear down the bottom here, but so it's running the tests over here. Let's bring this over. Build errors. Okay. What have so it's locked the file again, which is a real pain. So let's find that test. What was it called? Test host or something, wasn't it? Let's try and build it again. Yep, definitely locked it. So I think we're going to not use that test runner. Where's test host? Oh dear. Always unexpected issues, isn't there? So test host doesn't appear to be in that list. Which is a bit weird. Let's bring up Task Manager again. Very sorry about this. I can't see it in the list now. It was last time, wasn't it? We haven't got anything called test host here, have we? What's it saying is is hogging it? .NET Core host. Why is that hogging it? .NET, so this is one. I'll just make a note of that. 18716. Let's add the PID in. (18716). Can't even see that. Let's close Visual Studio again. I'm really sorry about this. Unexpected issues, but that's all part of being a streamer. No, I don't want to abandon the test, Ted. It's just that I don't want to restart the stream. It makes things a bit more difficult in terms of stitching the videos together. So let's see if we can rebuild now. So it's still grabbed by something. .NET Core host. How unfortunate. .NET Core host, there it is, let's kill that. What we'll do is restart Visual Studio again just for good measure. So I think there's a bug somewhere, whether it's a bug in my test runner or what, I don't know. I should be able to build now. Which we can, okay. So we set up our tests. These tests should now fail. So let's run through a different test run. Run all tests. And we've got a failure, which we expected, and it is with the load. But then didn't change the name, did I? Yeah, I need to change the name of it. But it is this one we just added here. This one we're adding 2 to 7F. It should load with what did we say? I think we said it would be. Where's my calculator gone? It was going to be 129, wasn't it? With 129. When adding 127 and 2. There we go. So we do get that failure we expected. So we need to set the S flag here. Just move that out of the way. Okay, so let's go and code that bit. So, right. So the S flag is fairly simple. It's got to okay. So what we can say is set flag and it's going to be flags S. like that. And so if the sum bitwise and with 80, if that's greater than 0, then that flag must be set. So we say true, otherwise it's going to be false. And we need to put brackets around that expression there, that conditional, that boolean. We're probably going to have to make this a byte, aren't we? Let's create it as a byte initially, and then we can get rid of that. Okay, and here it's saying, I think we need the brackets there, not there. There we go. What's n? So we need that to be a byte as well. Okay. So we need to cast that as a byte. So it is a bit problematic when we're working in C# with these different types. So no, that's okay. Change that to a byte. There we go. That's happy now. Let's rebuild that. Okay, hoping that everything's going to be okay with our tests. Let's run our tests again. Okay, so now passing. Okay, so what's the next thing we need to look for? Let's go over here. So we've done the S flag, the Z flag, and the N flag. Pardon me. So there's this. What's the next thing we do? Okay, the half carry. If there's a carry from bit 3, so if bit 3 carried over, so if there was kind of a 1 plus 1 in bit 3, and so it would carry to bit 4. So we can do that. That's fairly simple. Right. So there won't be such a thing here. Oops. So this is going to be the half carry flag. And there won't be a half carry, a carry across from bit 3 to bit 4 if we're adding 0 and 0. Okay, but what about this case? Adding 127 and 2. So let's have a look at what that's going to look like. Okay, let's see if we can do a bit of writing here. So we got 127, which is going to be 0, 1, 1, 1, 1. 1, 1, 0 plus 2. That's 0, 0, 0, 0, 0, 0, 0, 0. Not quite got those lined up, so let's just rewrite the top line. Okay, so that's going to be 0, 1, 1, 1. 1, 1, 1, 0. So let's add them together. So this is not 0. This is a this here. Here's a 1. So adding these together, 0 and 0 is 0. 1 and 1 is 1. Carry 1. 1 and 1 is 1. Carry 1. 1 and 1 is 1. Carry 1. 1, 1. So 1 and 0 and 1. So I've lost me way. Let's get a start again. Okay. So 1 and 1 is 1. 1 and 0, but we code a 1. 1 and 1 is 1, carry 1. 1, 0 and 1 is 1, carry 1. So we have carried across, the carry bit has been set. We're going to carry from 3 to 4. So we know now that this flag should be set in this case. So let's try this. So let's say that this should be true in the case of 127 and 2. Okay. Now we can bring that across and we can run our tests. And we get obviously the failure we're expecting. Okay. So let's code the carry flag, the half carry flag. Okay. So what we're interested in is the first 4 bytes, the first 4 bits of each byte. So as we saw here, we're only really interested in these parts. Okay, just those. So let's isolate those nibbles, as they're called. So what we can say, we can pinch the same kind of command, and this may not be good as a ternary command, but we'll struggle through. Okay, so we need to look at each of the individual nibbles, don't we? So if we'll say A, and we'll AND that with 1 1 1 1. And we'll add to that N masked off with the same value, and if that's greater than 1 1 1 1, then that should be true. Let's run our test and see if that's the actual correct thing. So what do we get in that case? Okay. Oh. So let's go back to drawing. So if we've got one, oops, let's go back to a decent colour. 1 1 1 0, and we're going to AND that with 1 1 1 1. So we're going to have 1 1 1 0 at that point. So that's the result of that AND. And over here we've got 0 0 1 0. Come on. We're going to AND that. Obviously we're going to get 0 0 1 0 from that result, and we add those two together we're going to get 0, 0, 1, 0. We're going to get 0, 1, 1, 1, 1. We're going to get the carry here. There's the half carry after. And that value there is greater than that. So what is wrong with our logic? So if A ANDed with 1111 plus N ANDed with 111, is that greater than 1111? If so, set the flag. So let's pull this out so we can debug it. Call that X. Okay. Let's pop a breakpoint there. And let's run our test in debug mode. Hopefully we will hit the breakpoint, but we may not. We may have to step into the code from the entry point. Yeah, we've hit it. Okay, so this is now 1, which is not what I was expecting it to be. So should I be doing that, for example? Debug again. It's still 1. Okay, let's try this. Go again. So what's X now? It's 3, really. The accumulator contains what? 129. It's got the answer already. That's the problem, isn't it? So we need to do this. We need to do this beforehand. So this won't be a problem when we do the refactoring, but let's move this line to there, set the breakpoint just there, and see where we go now. Okay, debug. So that's 17, which is greater than F, isn't it? So that now works. Okay, so if we continue that, I move the breakpoint and I continue, that test should now pass, which it does. Okay, so we've learned a valuable thing there, that we need to do this this check beforehand. But say that with the refactoring I've got in mind, it shouldn't actually be an issue. So we'll leave that as it is. Remember, we're doing the simplest thing that could possibly work to get our test to pass. That's half carries done, which is pretty good. Okay, the next one. So now we've got the parity stroke overflow flag. So this is basically going to be, in an addition, this is going to be set if the result of our addition is greater than 255, because we're doing 8-bit arithmetic here. Okay, so that should be fairly simple to set up. So we know that for all the calculations we've done so far, the overflow flag should not be set. So let's assert that to begin with. I can't remember what I called the overflow flag. Let's go over to our Z80 class. Overflow was it was the P flag, parity. Oops. Oh, if you do watch my shader streams, by the way, this is the latest version. It's actually a screen grab of the latest version of the terrain shader we're building, and it looks absolutely gorgeous. So I saved it as a screen grab and put it as my background. We sorted out the shadowing on the mountains, and now it looks really icy, and you get these gorgeous highlights. We're going to do a lot more with this shader in the next stream next Monday. So do join us for that. So okay. So we're going to go to our tests. So we were going to say, we're going to copy that one, and we're going to say that the P flag it's not going to be set by adding 1 and 2, 1 to make 3. It's not going to overflow. It's not going to overflow adding 0 and 0, and it's not going to overflow adding 2 and 127. So we need a new test. So let's grab this test and go to here. So now we're going to say we want to load. We want to add. So what do we want to add? If we add, so we add 127 and 127. So 127, 127. So let's have a look at that. So if we go to 127 plus 127, so that's not quite big enough. We need it more than that. So let's have 129 and 129. Okay, so 129 times 2 is 258 in hex. That's 102. So in fact, that's going to be 02 as a byte, and then we're going to have the overflow flag set. So we're going to expect to have it in here 2 and overflow. Okay, so 129 in there, so that's going to be 129 is going to be 81, and we want 81 in there, and we're expecting the result to be 2, and we're going to expect our overflow flag to be set. Okay, so what do we expect with the half carry? Well, I don't expect it to be set to half carry, and I don't expect the sign flag to be set because the most significant bit is now going to be a 0. So that should be false as well. Okay, so everything false apart from the overflow flag is what my prediction is. Let's run that suite of tests and see what happens. We'll just run the arithmetic and logic group tests. So we have a failure where we expect, so the overflow flag wasn't set. So let's have a look at the so assert true, expected true, got false. Okay, which is what we kind of predicted would happen. So this is obviously once again the red area. Now we need to do the green. Okay, so overflow. This overflow is pretty simple. What's the best way to do the overflow flag? Okay, so we're going to use an if statement for this because it's a bit more complicated. So we also need to do this before this is where we actually need Okay, we'll do the calculation first. Well, I'm just going to use silly variables y. So what we'll say is if a is greater than or equal to 80, okay, and n is greater than or equal to 80, okay, or no, it's not that easy because we're trying to do with negatives here. We're trying to look at the overflow situation where these numbers are negative, where the sum is negative. And let's just stop at this stage for now, and then we'll say we'll just copy this. And we need to refactor this. This is the parity overflow flag. This is going to be y, and so we will refactor this. So at the moment, this is going to be if both of the operands are greater than 80, then it's going to overflow. We know that. Right. Let's run our test. I think we're going to refactor next, I think. So let's see what happens with that test. So that now passes. However, I'm not happy with this condition. Mainly because are we dealing with negative numbers? Okay. So let's do a refactor at this stage, because I think what we can do this a bit. We can box a bit clever here. Okay, so let's imagine that we're going to pass in. We're going to have a function. The function is going to be an 8-bit addition function. So what we're going to do is we're going to say that the result is going to be equal to add 8, we'll call it, and we're going to take in two values. We're going to take in a and we're going to take in n. So let's create a method like that, and we'll put it there. Okay. So what's that method going to look like? Well, the first thing we want to do is actually add our numbers together. So we can say var sum is going to be a, and we'll change this to b rather than a plus b, and then we'll return that sum. Okay, so that's fairly simple, and we're going to cast the whole lot as a byte. Like that. Okay, so now what we can do is start to bring some of our logic down from up here. We can certainly bring all of these things back, pop them down here. This piece here, we can actually grab that piece of logic there, insert it back into there, and this is going to be A and B. And we can can grab this piece of logic and what's the best way of doing that? So let's make an if statement. We're going to say if, grab that, and that'll be A and B. And in the simple case, we can say set flag, and the flag was P, wasn't it? Set flags P to true, else set flags P to false. Okay, so now we can basically lose all of this. We've got a nice add function like that. Okay, so let's run our tests to make sure we haven't broke anything. So we should be okay. We are. Okay, so the refactor was safe. But what we'll do is just make sure, because lesson learned from making a simple change, let's run all of the tests and they all pass fine. Right, afternoon Cody Beard, good to see you. Sorry I didn't notice you in chat. Good to see you. You'll notice we've just we just achieved our follower target at 300 followers. So I was really pleased by that. It was Jitter Ted who was the 300th follower, so great thanks to him. Okay. Now this logic here I believe to be slightly incomplete. So let's consider the case where the two values individually are less than 80, but the sum at the end is less than 0. It's negative. So we could have the case like this, where these are less than those numbers, and sum, we better cast that as a byte. We'll do it for sum is less than 0. It's negative. See, sum is okay though, it's working because it's a byte there. So that's another condition where we will have overflowed. Okay, so I wonder if we can get a nice ternary expression out of that. Let's compress the ternary and see what it does. That's not too bad. If we make it a bit neater on the page, that might help. Okay, so let's run our test to make sure that still works. We'll run all the tests. Okay. So that's good. So that's 1, 2, 3, 4, 5 of our flags sorted. So what else is next? So there's a carry flag. So if we carried from bit 7, and that's quite simple. The carry flag, if the result is greater than FF, basically, the carry flag should be set. So let's just beef our test up. Oops, sorry, over here. So in the case so in our tests here where we're adding 1 and 2, that won't be the case. The carry flag won't set. So the carry flag won't be set. That's going to be a false assertion. And the same when we're adding 0 and 0. We're adding 2 and 127. It's not going to carry. And if we're adding 129 and 129, then we will have overflowed, and also we should have a carry, shouldn't we? So let's set that to true. And let's see what our test tells us is going to happen. Yes. So that's a failure, which is what we wanted to see. And we'll go over to here. And now in our add function we can do a very simple thing to determine the carry. So if the sum, if that is greater than that, we should set the carry flag, which is the C flag. Okay. So let's run that as a test. Oh, we've still got a failure here. So the carry flag wasn't set, so we didn't carry out of. We didn't carry. Okay, that's quite possible, I suppose. Let's go and have a look at that for first principles. So let's delete all this. Oops. 129 and 129 is greater than FF though, isn't it? So why didn't it set it? So the sum is coming through as, because it's a single byte, it's coming through as 2, isn't it? The sum is being cast as a byte there, that's the problem. So we need not to set it as, we need to not cast it, that's the problem. We need to cast it here once we've, so here it's going to be a int 32, which is fine. Okay, now that should actually pass, he said, hopefully, and it does. Okay, so we needn't to bother with that. Okay, so that's that. Now if we go back to our Z80 class, you can see here we've got the 8 flags which the Z80 has, and there's a couple which are undocumented. So there is this one I've marked X, and this one I've marked U. And so there's actually a document out on the internet called it's called Z80, the Undocumented Z80 Documented. And it's by Sean Young, and it's quite old now, 2005, but it's basically someone's gone through and looked at all the features of the Z80 that are documented and found out where actually they're not right. The documentation is either wrong, or there are features which happen on the actual chip which aren't in the documentation, and these 2 flags are part of that. So we've got a flag which is a copy of bit 3 of the result, and a flag which is a copy of bit 5 of the result, which is a bit strange that happens, but we're going to actually emulate that, because there may well be cases where people have written programs which rely on that. Who knows? So we want to emulate the actual chip as accurate as possible, even when if I find there are actually documented bugs in the Z80 programming language itself, the Z80 chip, bugs in the logic, we want to try and emulate those bugs as well. Okay, so Z80 instruction, we want to do the undocumented flags. So we're going to set flags dot X and U. Okay, so I've forgotten what they are already, so let's go back to our class. So we'll look X first. The X is going to contain bit 3. Okay, so bit 3. So if we've got, for example, if we've got 0, 0, 0, 1, 0, 1, 0, 1. Bit 3, this is bit 0, bit 1, bit 2, bit 3. That's going to contain a copy of this bit. Okay, so in order to find that bit, we want to mask our result with 0, 0, 0. Oops, for some reason I'm not getting very good. There we are. 1, 0, 0, 0. Okay, so in this case we're going to AND them together, and 0 and 1 make 0, so that bit is not set. If that bit was set, so for example, if I go up here, click on that, and if that was a 1, then 1 and 1 would make, ANDed together would make a 1, and we would set the value to that. So 1, 0, 0, 0 is the magic number here. So let's clear that. Go into binary mode. So 1, 0, 0, 0 is 08 in hex. So over here, what we want to say is, so if sum bitwise ANDed with 8 is greater than 0, then true, else false. Okay, that's the X flag. So we need a copy of bit 3. And here we've got a very similar piece of code. So let's just grab the whole thing. Copy in here. So this is bit 5 now. So let's have a look at that. Hopefully I better draw a bit better this time. Let's go over here and hit that. Right. And now what we want to do. So if we had 1, 0, 0, 1, 0, 1, 0, 1. We want to test this bit. This is bit 5, so bit 0, 1, 2, 3, 4. So 0, 1, 2, 3, 4, 5. This bit here. This is our what we're trying to target. Okay. So we want to mask it against 0, 0, 1, 0, 0, 0, 0. We're going to AND that together. In this case, it's going to be 0. So this number 1 with 4 zeros after it. Let's find out what that is in hex. One, 2, 3, 4. So that is 1, 0 in hex. So we do that. So a copy of bit 5. Okay. So let's have a think about what our test values are going to bring back this time. So the first one thing we can say is that that's not going to happen. Those aren't going to be set when we're adding 0 and 0. so we can assert quite happily for that case. So we're adding 0 and 0, which is here. 0 plus 0 is 0. We can quite happily assert that x and u are going to be false. Oops. Like that. Okay. So, what about in the case when we're adding 1 and 2 to get 3? Well, that 3 doesn't have bit 3 or bit 5 set, so they're going to be 0 as well. So we can quite happily say those are going to be false as well. Okay, so we're going to have 129. We're going to get 129. So let's have a look at the result of 129. And we can bring our calculator over, and this will help us see exactly what's going on. So we'll clear that. In decimal, 129. In binary is this. So this hasn't got bits 3 or bit 5 set either. So we can quite happily copy that down. Yeah, they're not set. So, and if the answer here is 2, 2 definitely hasn't got that set. So we're going to want to have some new tests to determine whether this is working or not. So, let's have a look at what we can test. So what number can we, let's go into binary and clear this. So we want something where we've got 0, 0, sorry, we want 1, 0, 0, 0, 0. So that number as the result. So if we added 8 and 8, that should set bit 5, shouldn't it? Let's try that. So that'll be 16. We added 8 and 8. Okay, so this is going to be 8. So 8 is going to be, so let's just show you, so we just not mess around, let's just show you exactly what it is. So 8 in decimal is going to be in hex 08. And into our accumulator we're going to load 8 to begin with, and our result then should be 10. Okay, and in this case we expect the flag bit 5 to be 1, and so our undocumented, I think it's the U, I can't keep it in mind, the U one, yes, the flag U should be set in this case. So we're going to say true here. However, we don't think there's not going to be a carry, and there's not going to be an overflow. So we believe that that is the state of the registered having added 8 and 8. So let's run that as a test and see what happens. So, CodeBed, you just got off an hour-long conference call which consisted of you pointing out the supplier had messed something up, followed by 50 minutes of silence. So 10 minutes of that and then 50 minutes of silence. Yes, that's an interesting day for you. So we got a failure there. So why have we got a failure? So what's it saying? So it's expected false when it's actually true. So have I got the wrong flag? I think it's the wrong flag, isn't it? U. I thought U was bit 5. Oh no, it isn't. So it's wrong, isn't it? That's not correct. We don't want to add 8 and 8. That's silly. So let's get the data correct first. So it's going to be. Let's have a look. Clear this into binary 1 and then 0, 1, 2, 3, 4. It's going to be that number, which is 32. So we want to add. I don't know. Should we add 2 and 30 together, something like that? So 30 in hexadecimal is 1e. So let's add 2 and 30, and the answer is going to be 32. So it's silly, bad data. So it's going to be 32, and when we add 2 and what did I say? 30. Okay, move that out of the way. So we're going to add 2, and we're going to have 1e in there, and the result's going to be that. So let's run that again and see what happens. Oops, we've still got the same problem, have we? So 2, 0, 0, 1, 2, 3, 4, 5. So that is definitely set. So let's go and have a look if we've got our code wrong. So we're fairly sure the data's correct now. So it's not going to be 10, it's actually going to be 20, which is the result there. And let's run that again. Are you going to build? Come on. What did I make? Yeah, it's decided to can't access that thing again. Being plagued today by weirdness. So what is stopping it? The .NET Core host 19032. How strange. .NET Core host. There it is. You can go away. And we'll run you again. So it's still failing. It's still saying that the expected false and the actual was true. Expected false, but it was true. I wonder if it's another one of these. So was there a carry? There may have been a carry. So let's go and we'll look at the actual calculation itself. So what do we have? We had 2 and 30, didn't we? So let's get rid of this. We changed the numbers, unfortunately. This is my problem. So let's see what the result is. 32. So in binary we're going to add 30 and 2. So let's we know what 2 is. So 2 is 0, 0, 0, 0, 0, 0, 1, 0. That's our 2. We're going to add to that 30. So what's 30 in binary? Let's get, that's 1e, isn't it? So let's put in 1e. Oops. 1e. And that's that there. I'll just move it off the screen so I can copy it in. So that's going to be 0, 0, 0, 1, 1, 1, 1, 0. Let's add those together. So 0 plus 0 is 0, 1 plus 1 is 1, carry 1, 1 and 1 is 1, carry 1, 1 and 1 is 1, carry 1, 1 and 1 is 1, carry 1. And that's 1, 0, 0. Is that right? That's not right, is it? 1 and 1 is 0, carry 1. So I've got that completely wrong. Let's start that calculation again. So, there we go. That's 0, carry 1. 1 and 1 is 0, carry 1. 1 and 1 is 0, carry 1. 1 and 1 is 0, carry 1. That's better than 0 and 0. So we've had a carry, we had a half carry, didn't we? We had a carry from this bit here, bit 3, 0, 1, 2, 3. There was a carry across. So the half carry flag is set in this case. So we need to go here and find the half carry and say that's true. And let's see if that is a winner. Yay, that's it. So there was a half carry that got us. Okay. So that is the bit 5 being copied across. So let's do bit 3. So we expect this to be false this time and this to be true. So bit 3 is going to be set, we hope. So let's figure out some data that we can get for that. So the result we want is going to be having bit 3 set and then bit 2, bit 1, bit 0. So this is the bit that's going to need to be set. So that is F, isn't it? That's F. No, it's not F. Ridiculous. That is not F. That's 1, 2, 4. That's 8. Okay, so if we added 4 and 4, we should get a result like that. So 4 would be 0, 1, 0, 0, 0, 1, 0, 0. Add those together. We get 0, 0, 0, carry 1, 0, 0, 1. So there's no half carries, and that should be straightforward. We should be able to detect that bit 3, bit 0, 1, 2, 3 is being set. So we're going to say 8 when adding 4 and 4. So I'm going to put 4 in there. I'm just going to correct that documentation we did here. This is going to be 2. And in the accumulator we'll put 4 as well. We expect to get 8. We don't expect the half carry flag to be set this time. We just expect undocumented register 8, register X to be set. So let's run that. Okay, so that's working. So now we have a quite robust set of tests which are making sure that we are setting all our flags, our condition flags, correctly. And that's quite a nice position to be in now. The reason why it's in quite a nice position to be in, because now we can go back and look at our instruction. Okay, so we've got this add8 command, add8 method. If I go over to the documentation here, we've got this add the value n, add a and n. If I go down a bit, where is it? There. Okay, there's this command here, adc a comma n, and what that it says basically is do an add of add the accumulator and n, but also include whatever value is currently in the carry flag, and that is CE is the opcode for that. So we could get relatively free an ADC command here. If we pass into here byte C equals 0, we haven't changed our logic at all, but we could add C in there where C is the value of the carry flag. Now we can run our tests again to make sure nothing's happened. And it hasn't. But now what we can do, we can grab this command, and instead of AD, it's now going to be ADC. We're not going to change anything other than that, and we're going to go over to our Z80 class over here, and we're going to add that into our command. This was CE. So here's C6, which is our add A and N. We're going to just drop that down, change that to CE. Oops. Change that to CE. And that's going to be ADC. And that's going to be ADC. Okay, so now we can just repeat all of our tests. So let's copy all of those tests and just double them up. Okay, so now we need to go to the first place where we got a problem, and that was good. It was adding 1 and 2, wasn't it? Where is adding 1 and 2? There we go. This is going to be ADC now. And this is going to be CE. That's going to be ADC. ADC. CE. ADC. ADC again there. CE. ADC. And the same here. Like that. And here. CE. And the last one. ADC. ADC and CE. Okay, so before we do anything, we're going to just run all those tests again. Okay, so we've got all set of passing tests. Now of course ADC and AD are now doing exactly the same thing. So we need to change what ADC does. Go in here. So ADC, we need to actually pass in the value of the carry flag. So in here we can say C. We can pass that in. So that I thought it's a byte. So so we can say C equals like that. Well, let's pull it out, and these need to be cast as bytes, do they? So we'll just do the simplest thing that will work, which will be that. And we'll pull that lot out. And we'll say byte C is equal to that. In. Okay. So now we run SS again. And they all pass. So we don't need to go through a whole rigmarole of all these tests, writing all these tests when we got the carry flag set. We should just be able to get away with passing, you know, one value in, I think. So let's go over here and just do a fairly simple one. So we've got 4 and 4. Do that one. See what happens. So we're going to want, we got 4 in there, and we want the carry flag to be set. Okay, we need to work out how to set the carry flag, but that's okay. So we expect we get 9, and we'll say and carry flag set. I like that code which is highlighting my spelling mistake there. That's always a good thing for me. Okay, so we're going to expect to get 9 out of this because we're going to set the carry flag. So, carry flag, let's go and have a look at our Z80. Pure Snable, notice terrain shader isn't compatible with Edge. No, it's not. I've noticed that. It works great in Chromium Edge. It's quite easy to fix, is it? Okay, we probably do want to fix it. It works great in Chrome and Chromium Edge. So, I'm just trying to show you Pure Snable. I've set that as my backdrop. Times 0 on the shader is now my backdrop because I think it's gorgeous. It looks like a painting. As I posted in Discord, up the Lonely Mountain. Changed 2.0 F to 2.0. Okay. Yeah. Interesting. Right. So we need to set that flag. So what is that flag? It's the carry flag is the first bit, which is great. So what we should be able to do now is to set, go over to here, we should be able to say that F, which is our flag register, is that. Oops. I know what I'm doing, Code Rush, don't interfere. Cast it as a byte. Really? So why is it complaining about that? If it's a flags type, okay. So how am I going to set the carry flag? How am I going to set the carry flag? Can I do it like this? Oh, dear me. This is where sometimes when you get things trying to help you out aren't quite what you want. That's going to be helpful. Okay, so that seems to be the way to do it. So let's run this test. It's this one here we're interested in, and it failed. So it actually had 8 in, so I don't think I managed to set the carry flag by doing that. So let's go and have a look and see what happens. Let's pop the breakpoint there and debug it. Let's see, it's definitely 0. It's false. Okay. What is my flag thing called? Move that out of the way. Check flag. And this is going to be flags. See. Let's run that again. And there we go. My test in there was wrong. So we got that passing there. Okay, I think that's probably a good point to wrap up the stream. We're going for just over 2 hours. So let's go and try and find someone who we can raid. First thing we'll do is to make sure everything builds okay, and then we'll push this up to GitHub, where all the code is available to have a look at. So, episode 68. Commit that. And sync it up to GitHub. So that'll be there in a few seconds. In the meantime, let's go and find someone who we can raid, shall we? Switch. Well, we've got Mark Miller. We'll go and raid Mark. If you haven't been seen one of Code Rush's streams, then do stick with this. It's fantastic. He's working on like a D&D special effects kind of program, which is fantastic. All integrated for his stream. So let's go and rate him. So the next planned stream will be on Monday. You never know, we might have something in between, but Monday should be another shader stream with Fuel Snowball. So I'll see you then. So take care, everybody.